Hello and welcome to part 2 of lecture 2 of ENGR 2301 Engineering Statics. In this part of the lecture, we're going to look at defining ways of representing vectors, and then in the later parts we will look at some basic vector operations. So let's talk about ways to represent vectors. And again, you may have seen many of these things before in previous coursework, but I intend this to be a review session, a tool of review. That'll be very useful if it's been a while since you've had some of this earlier coursework. So, ways of representing vectors. So, first I'm going to start with 2D. Let's first talk about 2D vectors. Now, we could talk about a trivial case of 1D vectors, but a 1D vector is almost a scalar quantity at that point, so let's not worry about such things. So 2D vectors. Let's look first at 2D vectors. Your 2D vectors, there's going to be two main ways of representing them. The first way is going to be your polar form. And this represents your vector with both a magnitude and a direction. A polar form represents your vectors. Vectors with a magnitude and a direction. Both a magnitude and a direction. So we'll have both a magnitude and a direction. And so this really represents sort of the vectors in their purest form. We say, in the previous portion of the lecture, we defined a vector as that which has both a magnitude and a direction. And really, I think of polar form of vectors as the vectors in their purest sense. We say a vector has both magnitude and a direction. And in polar form, we represent that as it really is. So if you have, say, a set of axes here, x and y, and then let's say we have a vector, and I could define this, say, I don't know, as, let's go right to force vectors. Let's say this thing has a magnitude of 5 newtons, and it's at an angle of, say, I don't know, let's say 30 degrees from the horizontal. I could represent this, and let's say this was let's say I wanted to designate this vector A. If I was writing this in polar form, I could say that vector A is equal to 5 newtons at an angle of, and I probably wouldn't use the brackets there, I could just say 5 newtons at an angle of 30 degrees. And this is, if I didn't want to use absolute angles, I define absolute angles as those that are on a 360 degree. If I wanted to use relative angles measured off of a nearest reference axis, I could say, I could represent this as a couple ways. One is 30 degrees, or I could say 30 degrees above the positive x-axis. The positive x-axis. That is representing this as a vector in polar form. What happens if I have something that's in a different quadrant, though? So let's say I have a vector O of 6 newtons, and maybe this is vector A, or vector B, I should say. And let's give this an angle of, I don't know, maybe 60 degrees from here. Let's say this is 60 degrees. 60 degrees. And in turn, I could say that vector, I keep wanting to call it A, but B, vector B, would be, I could write this two different ways. I could not simply write this as 6 newtons at an angle of 60 degrees. That really doesn't work, because if I don't give any axis, any reference axis, and if I don't give any reference axis, I am going to assume that I'm taking that off of standard, or I'm taking that according to standard nomenclature or standard definitions. And if you remember back to your pre-cal and geometry, the standard way of measuring an angle, of course, is 0 along the x-axis, counterclockwise positive. So if you tell me 6 newtons at an angle of 60 degrees, I'm going to assume you're talking about a vector of 6 newtons at about right there or so. So we can't just say 6 newtons at an angle of 60 degrees, but instead I'd have to do two things, or one of two things. I could say 6 newtons at an angle of 60 degrees below the negative x-axis. And this would be sort of using a relative angle to describe where my vector is. Or I could say 6 newtons at an angle of 180 plus 60, or 240 degrees, if I was using absolute angles. And either would be acceptable. This one is fine, and this one is fine, but this one is very much not fine. So then let's look at the alternative, which is radial form, which is Cartesian form, or rectangular form. And another word for polar form would be your radial form. You sometimes see that as well, radial or circular form. There are many different ways of describing these things. Then we also have our rectangular form, ways of representing vectors. And this represents the vector via individual magnitudes with no angles. Here you represent the vector via two magnitudes on perpendicular axes. A set of perpendicular axes. So, if I have a something like this, if I have this, let's look at these same ones. Let's do these same ones again. And look at how I could represent these in rectangular form. So 5 newtons and 6 newtons. This is vector A, this is vector B, and we'll have the same relative angles. So let's say this is 30 degrees, and this is 60 degrees. 60 degrees here. And then let's write these in rectangular form. Vector A, and here I will use brackets because I'm representing it in rectangular form. I would call this 5 newtons, cosine 30 degrees, comma 5 newtons, sine 30 degrees. Very simple, basic math. And then vector B would be, for the x component, I would need to tack on a, oh, I'm missing my head on my arrow there, so let's go ahead and add that back. Vector B, I would need to add a negative on the x component if I wasn't using global angles. Now, if I was using global angles or universal or standard angles, if I'm using the 240, I don't need to worry about tacking on a negative, but if I just want to use the 60, I would need to say this is equal to negative 6 newtons times the cosine of 60 degrees. Or I could also just use the cosine of 240 as well. Negative 6 newtons times the cosine of 60 degrees. And this, the y component would be negative 6 newtons times the sine of 60 degrees. Or I could use the sine of, that would be 240 degrees. Either one would be acceptable. No great surprises here. And then some alternative names for rectangular form. I can also define this. You often see these referred to as Cartesian vectors or Cartesian coordinates, or sometimes component form. And really, by this time in your education, I would think you've seen these before in pre-cal, and hopefully you're all fairly familiar with it. In this course, when you hear me talk through the lectures, I will use the term rectangular, Cartesian, and component really interchangeably. I'm not picky at which I use. Same thing with polar or circular. Well, actually, I tend to stick with polar, but if I use those, I tend to just use those a little bit interchangeably. By the time you get to this level of your education, I would hope that you are familiar with what those mean in terms of coordinates. Anyway, representing coordinates and angles, etc. Okay, let's see. I'd like to give another note on rectangular form in terms of the layout of the axes. Layout of the axes. So, rectangular form or Cartesian form, choice of axes. Choice of axes. And this will be very important as we go later in the semester, especially when you start talking about local axes and a local axis, a set of local axes or axes, I suppose. A vector can be broken down into, now we tend to think of breaking a vector down into an x and a y axis, but what we call an x and a y axis really is pretty arbitrary. An x and a y axis really just mean any two set of mutually perpendicular axes. A vector can be broken down or represented as a set of any, or as components along any two perpendicular axes. So for example, let's say I have a simple vector. In fact, I might even work through a numerical example here. So let us say I have my standard x and y axis. Maybe I'll make this a little bit bigger here. The standard x and y axis that you're used to seeing, with x more or less along the horizontal direction, assuming you don't have your computer screen tilted at some weird angle. That would be pretty weird. That would be pretty weird. I don't know. Imagine any of my students like to sit there with your computer monitor at a 45-degree angle, but who am I to judge? So, anyway, let's say we have an angle here, or a vector here, and this vector is, say, 12 newtons at an angle of, I don't know, let's say 45 degrees. 45 degrees above the positive x-axis. Now, if I wanted to represent that in the x and y vector system, that'd be fairly straightforward. Components in along xy vectors, or xy axes. Because I picked the nice 45-degree angle, these would actually be the same. It would be 12 newtons, and if this is A again, vector A would equal 12 newtons, cosine 45 degrees, comma 12 newtons, sine 45 degrees, but these would come to exactly the same thing. So that would be root 2 over 2, so that would be 12 root 2 over 2, comma 12 root 2 over 2, or I guess that would be 6 root 2 newtons along both axes, and you could convert that to decimal if you wish, along each axis, and fairly straightforward. That's what you're used to seeing. That's fairly familiar. That there's no great surprises there. But what if I wanted to look at a different set of axes? So let's say for whatever reason I was interested in the components of that force along a different set of axes. And while this may seem arcane or very obtuse or very, kind of academic, a very academic exercise, In truth, this is something you do quite a bit in other courses or in other fields. And actually, we'll see this even in many areas of statics. You do this a lot in things like mechanics of materials. So you do instructional analysis. For example, in structural analysis, we look at things such as forces along member local axes. And we do this kind of thing all the time. And same thing when you look at dynamics of machinery and mechanical engineering. This is something you do quite a bit. So while here it's a very academic exercise, in reality, you do this quite a bit. So let's consider this. Let us consider a set of rotated axes. And let's say I have another x-axis, and to not get too confused, or not to get too mixed up here, I'm going to call this an x prime axis. And let's say this thing is at an angle of 30 degrees from the x-axis. So now, remember, I said that they can be represented by any two perpendicular axes. So I can't just decide to represent this as a y prime axis just off at any old angle. If x prime is going to be here, then y prime really should be up here, if I'm talking about simple rotation. A simple set of rotated axes. We could talk about more advanced transformations at another time, but in terms of simple rotated axes, these two really do need to be perpendicular like this. So what this does, though, is this dramatically changes the angle. This dramatically changes the angle for my system here, or for my vector here. And so now the angle from the x prime axis is no longer 45 degrees. What is it? Let me do this maybe in, a nice blue would work. So instead of being 45 degrees, it is the difference between this. It is now 45 minus 30, or just 15 degrees. Just 15 degrees. So therefore, and this can be really fun if we start dealing with negatives and things like that, but let's just keep things relatively simple right now. A then, vector A, would be equal to 12 newtons times the cosine of 15 degrees, comma 12 newtons sine of 15 degrees. We would have a different angle that we'd need to worry about. And this one is fairly simple because we're not actually, this is not going to become negative, or none of the components become negative. But if I rotate this quite a bit, then things can get kind of interesting. So let's actually look at that. Let's say I do one more, maybe another set of rotated axes, to show you how that would work. Let's say I have and this diagram is going to get a little bit crowded, but thankfully I have a nice color palette to work with, so hopefully it won't get too confusing. So in the theme of using prime, why don't I just use a double prime, like I was doing a second derivative or something. So let's say I did that, and then maybe I have a y double prime axis here. Y double prime, and then this is not to scale, that's a also perpendicular. This angle is definitely more than 90 degrees for the blue as I drew it, but the relative rotation should be fine. And let's say this was at an angle of, let's say this angle here was at, I don't know, 60 degrees. 60 degrees here. So this diagram is getting a little bit complicated, so let me go ahead and just isolate the x double prime, y double prime set of coordinates, or set of axes, or coordinate axes, and that'll allow us to really suss out what's going on here. So you have the x double prime and the y double prime, and if you look at this, our 12 Newton vector is now below the x-axis. So we have a 12 Newton vector here, and let's think about what this angle is going to be. This angle is now 15 degrees below the axis. So if this is 60 degrees from the x-axis, the global x-axis to the x double prime axis, and this is 45 degrees to the vector here, that means the angle from here to here is 15 degrees, which means this has an angle of negative 15 degrees, or just 15 degrees relative angles here. 15 degrees reference angle. And so then, if I was using reference angles, and I just wanted to apply negatives as appropriate, so maybe I can put an A prime and an A double prime. This would be equal to, that would be 12 times the cosine of 15 degrees, so the same thing there, no change. However, for the y, I would need to add a negative onto it. Negative 12 times the cosine of 15 degrees. Negative 12 times the cosine of 15 degrees. So the key here is that we can see that we can represent a vector along any set of perpendicular axes. Any set of axes will work. I can choose anything along the coordinate plane. What is key, though, is that they must be perpendicular. I can't choose one axis that I can't choose an x-axis like this and a y-axis like this or something. They have to be perpendicular with each other. That is what the key point is if I'm trying to represent Cartesian vectors in a 2D plane. So next, I'd like to talk about ways of representing 3D vectors, and I'll briefly talk about this because we're going to deal with this more when we get to 3D vectors in the next lecture or two. So ways of representing 3D vectors. And there are basically three ways of doing this. There is one, the Cartesian. And this is where you represent your vector with so you have a force F. Maybe I would represent this as an Fx component, an Fy component, and an Fz component. So I would have a set of axes, x, y, and z. And then maybe I have my overall vector, my, or maybe for example, a force or just a generic vector A. And that generic vector A would have some component AX, AY, and AZ. AX, AY, and AZ. So vector A is equal to AX, AY, and AZ. And notice when I'm writing these out, when I'm writing the variables for my components out, I generally don't write a vector sign above these, and that's because the individual components of a vector are scalars. In Cartesian form, vectors are made of multiple scalar quantities. And the same is really true for polar form as well. So that's one way of representing a 3D vector. And now, in terms of representing the equivalent of the polar form, now the Cartesian is the simplest one because it's, or the simplest to directly conceptualize because, if you have a Cartesian 2D vector, it's very simple to think of just adding another third dimension. Oh, now we have not only x and y, but we have a z, so fairly simple. But transforming the polar form into a 3D form is slightly more complex. And the reason for that is that you can't, if you think about 3D space, you cannot represent a vector, a 3D vector, via a single angle. It's simply impossible. You can't measure one angle off of a single axis or a single point and describe a vector in space with just a single angle. So there are two different ways of doing these. The first one would be spherical. Spherical representation, or the spherical form. This would be one magnitude, two directions. So maybe you would have an x, a y, and a z. And not every book puts the y-axis here. Sometimes you have the z and the y-axis switched here, so hopefully don't get too hung up on that. But we'll get to that more when we look at 3D vectors in the next lecture or two. And so you have your vector A. Say you have your vector A. Well, you would still have the magnitude, so you would say that vector A equals some magnitude of a. That's not going to change. But then you would maybe have two angles. Maybe I could represent this using some sort of brackets. Maybe I could say this is a magnitude, an r, a theta, and a phi. And so, for example, I would need two different angles. Let me maybe describe these in a different color, write these in a different color. Let's say I had a theta, which was an angle along the xz plane. And so I would have some angle theta like this. And then, so there would be, I would basically find the projection of this down upon the xz plane, and then I would find the angle to that. And then I would, in turn, measure the angle up to the vector, and I would call that perhaps a vector phi. Although depending on your particular coordinate system, you might have theta and phi switched. So I would use basically two different angles to fully represent where this vector is in 3D space. I would have one vector basically along the horizontal plane, one angle telling me where this thing is along the horizontal plane, and I would have another vector basically telling me where this vector here is, or I should say another angle indicating where this vector is above or below the horizontal plane, and that's a spherical representation. And then 3, I could use a cylindrical form or cylindrical coordinates. Cylindrical form. And I kind of think of this as two magnitudes and one angle. Two magnitudes and one angle. So if I draw out my coordinate system again, say x, y, and z, and I have the same vector a here, vector a here, I would say vector a was equal to three things. I would have my magnitude of it, its actual size, then maybe a height, and a theta. And what that would mean is, well, I would still have the projection of this down along the xz or whatever coordinate system you're defining for your horizontal plane. And then I would have some distance, not this angle here, but a distance above that. So I would have this angle theta, and then some distance h above the horizontal plane. And that's basically how you represent this. If you're representing things this way, we refer to this as cylindrical form or cylindrical coordinates. So basically you have your an angle that tells you where you are, basically where you are along, or what angle you are along the plane, and then you have a height and a hypotenuse to tell you everything else you need to know about the vector. Now, that's all well and good, but I would tell you not to get too hung up on the cylindrical and the spherical forms. It is very rare. Now, you sometimes see these in mathematics, you sometimes see these in physics. There are some particular systems in physics, some particular cases in science classes and mathematics courses where these can be useful, but I will tell you that in this class, the only one that we are going to use is the Cartesian form of 3D vectors. So don't get too caught up in worrying about the 3D forms of the spherical and cylindrical representations of 3D vectors. In this course, the only 3D vectors we're going to work with are going to be Cartesian, although for the 2D, we will sometimes work with, especially early on, the polar form. So the final thing I'd like to talk about in this portion of the lecture is how to convert between polar and rectangular form. So I want to look at how to convert between polar and rectangular forms of vectors. So let's look at that. So, and I'm going to focus particularly on the 2D form. In a later lecture, we'll look at conversions or resolution of vectors into components for 3D, but today I'm going to stick with 2D. I just wanted to include the 3D to be comprehensive when I was really defining vectors in this lecture. So conversions, or what's often referred to as resolution of 2D vectors, or I should say conversion, that would work fine. Conversions / resolution of 2D vectors. And what I mean by this is, if I have vectors in polar form, how do I go to Cartesian form? If I have vectors in Cartesian form, how do I go to polar form? Or basically, how do I go back and forth on a whim between different forms of vectors? So let's just break this down into two cases. Case 1, or the first one, would be, let's say I want to go from polar to rectangular. Although first, I might draw a little diagram. And maybe I'll start with a set of axes. The x and the y. And let's say I have a vector with a magnitude of a. This vector is going to have a magnitude of a, and it will have an angle theta, and it will have components ax and ay. So a with ax and ay. And then let's look at the two different cases of converting between from polar to rectangular or rectangular to polar. So let's look at polar to rectangular. So let us say that I want to go from, or let's say I have, or in other words, like what I'm saying is I have a and theta. I have a and theta, and I want to convert to ax and ay. I have a and theta, and I want to go to ax and ay. So think about this for a moment. This really is a simple triangle at this point. I can start by just applying some basic trigonometry, and I can say, oh wait, look at this. If I calculate the cosine of theta, well, I remember my trigonometry, I remember SOHCAHTOA. I still remember my grade school geometry classes and trigonometry, and so I know SOHCAHTOA, and so I know that cosine is equal to adjacent over hypotenuse, and that's going to be ax divided by a, or simply, of course, our classic ax is equal to a cosine theta. I've already been applying this earlier in this part of the lecture. You may have seen some. You already saw this a bit previously when I was finding individual components, but let's just explicitly define it here. Then I could also take the sine of that angle, sine of theta, is equal to ay over a. And if I solve that for ay, I get that ay is equal to a sine theta. And depending what vectors you're using or what kind of coordinate system you're in, you may need to tack on angles, or may need to tack on negatives to add negatives if using relative angles or using reference angles. So for example, when I say reference angles, again, I'm talking about if you are just defining a vector off of the positive x-axis, the negative x-axis, the y, or positive and negative y-axis. But if you're using a global or an absolute angle, like an angle that goes from 0 to 360 degrees, if you're using an angle of 225 degrees, well, then you don't need to tack on negatives depending on what quadrant you're in. I usually do that just because it's simpler for 2D problems rather than using the angles and worrying about what's the domain of arc, tangent, and things like that. But if you're just using global angles for this, you don't need to worry about that. But if you're using the relative angles, which we often do, you need to add on negatives as appropriate. Next, let's look at the second case, which is rectangular to polar. Rectangular to polar. So here we have we already have the rectangular. We have the AX and the AY. And we are trying to go to an A and a theta. We are trying to go to an A and a theta. And so, how can I do that? Well, the magnitude, this is fairly easy. This is actually fairly trivial. To do that, all I have to do is say, oh, look, A, or I can just apply the Pythagorean theorem. I remember my old buddy Pythagoras, and my old buddy Pythagoras, well, I shouldn't say my old buddy Pythagoras, I'm old, but I'm not that old. And so my old buddy Pythagoras taught me that a squared plus b squared is equal to c squared, or in the variables we have here, ax squared plus bx squared, or actually, sorry, ay squared. That looks like a t almost. That's a x here. Ax squared plus ay squared is equal to a squared, or that leads us to a is equal to the square root of ax squared plus ay squared. The square root of ax squared plus ay squared. I'm going to go ahead and box these for emphasis. And then let's say I want to get the angle. Well, for this one, it's going to be fairly simple. I can just say the tangent of theta is going to be equal to opposite over adjacent. So that's going to be ay over ax. Ay over ax, or simply theta is equal to the inverse tangent, or the arctangent, the inverse tangent of ay divided by ax. Ay divided by ax. No great surprise there. Ay divided by ax. Okay, so although you do have to be very, 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 very particular with this. So let's see. So why do you have to be very particular with this? Well, let's consider something for a moment. This is one of those things that you really have to be careful with, because if you're not careful, you can end up really screwing up the signs. Not in terms of sines and cosines, but in terms of positive and negative. And because of this, it really comes down to, and the reason for this is the domain of the arctan function. So I'm really getting into the nitty-gritty or the weeds of pre-cal here, but this is one you have to be very careful with. I'll just give you a little note here. Be very, very careful with the tangent, the arctan function, or the inverse tangent function. And as a reminder, the reason for this is the domain of this function, the domain of the arctan function, is not over the entire coordinate plane. It is only from negative 90 degrees to 90 degrees. Or if I was doing this in radians, negative pi over 2 to pi over 2. You have to be incredibly careful with this. And let me illustrate why. Let me illustrate the problem with this. Or another way of thinking about this is the arctan function. If you want to think about the function in graphical form, it repeats every 180 degrees. There is not a one-to-one mapping of the arctan function to the full unit circle. And this has, so all this stuff in pre-cal you thought you would never see again, it does actually have real implications for actual engineering design. So let's think about this for a moment. Let me give you an example here. I see this all the time in exam problems. It's a kind of thing that people make very common mistakes with, and really where this catches people is people who are used to using global angles, or people who are used to using global angles, because this is one area where global angles really does fail you, because if you're used to really using the blind plug and chug global angle method, this is something that's really gonna hurt you. So let's say we have a vector like this. Let's say we have a vector, or better yet, let's say I am told that vector A, has components that are, oh, I don't know, let's say -5 newtons, comma, 6 newtons. Or -6 newtons, that's fine. So where does this lie? -5 newtons, comma, 6 newtons, and I tell us, let me give us what, so maybe this is given, and find A in polar form, or sorry, yes, A in polar form. A in polar form. You know what, actually, let me go ahead and make this positive 6 newtons to make all sorts of trouble, make double trouble. So let's say I want to find vector A in polar form. And let's say I have my x and my y-axis here, and some nice axis arrow heads here. So I want to find vector A in polar form. Now, let me go ahead and plot out these components. So -5 and 6. Well, if I were to draw these out head to tail, I would have the x component like this. Here's the -5, or just a 5 here, or however I want to think about it, -5, and then upward 6. So I know this really needs to be in the second quadrant. But, so first of all, the magnitude is going to be trivial. That's not going to be a problem. You're squaring everything, you're canceling out the negatives. The magnitude is not what's going to get you. The angle is. So the magnitude of A, the size of it, that's trivial. That's just the square root of 6 squared plus 5 squared. I can throw that into a calculator really quickly and get the results. Let me just go ahead and do that. So that's the square root of 6 squared plus 5 squared. And that comes to 7.81 newtons. And notice for the angle, I deliberately chose something with a theta well outside of our domain for the arctan function. So the A is fine. Again, that's a magnitude. That's not going to have any problem. Now, what about the theta? And this is where people really flub up. Very common. And the reason for this is one of the most dangerous things you can do as an engineering student, or most common mistakes, but especially as a practicing engineer, one of the stupidest, most foolish, most dangerous mistakes you can ever make as a practicing engineer is to blindly throw numbers into an equation. By the time you get to, especially by the time you finish engineering school, nobody can get through engineering school without being able to trivially throw numbers into an equation. I don't care how complicated the equation is. I don't care if there's all sorts of arctans and natural logs and exponents and everything else. By the time you get through engineering school, there is no way you're going to graduate if you can't at least, throw numbers blindly into an equation, plug and chug, throw them into a calculator, and get the right number spat out on the other end. That is trivial. Most high school students can do that. By the time you get through engineering school, you can do that in your sleep. But again, one of the easiest ways to kill someone as a practicing engineer, this builds up in our previous discussion in lecture 1 about engineering models and their applicability, is to blindly throw numbers into an equation. And this is an example of that. If you do not know where this theta, if you do not know the limitations of the arctan function, if you just blindly throw numbers in here, you're going to get an angle that is not correct. And let me show you what that does. Let's show you how to do it. Let's see how to do it. How to do this wrong. The wrong way is to blindly apply the equation. Theta is equal to the inverse tan of, remember we said AY over AX. Fairly straightforward. AY over AX. And so basically I'm looking for a theta. The theta I'm looking for is right here. Or perhaps what am I looking for? Let me maybe do this in a different color to remind us what kind of theta we're looking for. We are looking either for a reference angle here or a global angle here. I'll take either one of them properly defined. A global angle measured from 0 to 360 degrees, or a reference angle measured off of the negative x-axis. Either is appropriate. But I chose this example because this will give us one that is correct in neither. So let's go ahead and do that. AY is going to be, so we'll have the inverse tangent of, that's going to be 6 newtons, and AX is going to be -5. So this is the inverse tangent, the units cancel out, of 6/5. Actually, sorry, -6/5. -6/5. And if I just, let me make sure my calculator's in degree mode, and it is, so I'll just keep it in degrees to keep things simple right now. And if I just say, oh, just sitting here whistling and not knowing what I'm doing, and I'm just, or maybe I'm rushing through an exam, I don't care, everything's fine, everything's hunky-dory, I don't care, I don't know what my equations mean, everything's fine and dandy, I'll just go ahead and throw that in my calculator and assume it's correct. Oh, I get -50.19 degrees. And then I just go ahead and happily report that, oh, vector A, that is equal to 7.81 newtons at an angle of -50.19 degrees. This is how you get my exam problems wrong. This is not correct. Maybe I'll do it in a different color. Actually, let's do this in like blood red just to really indicate this is not correct. Just a big old bar through that. That is not correct. And the reason for that is that if I'm given an exam problem, I will accept either one of these. I'll accept a reference angle or a global angle. But if you report 7.81 newtons at an angle of -50.19 degrees, what you're telling me is one of two things. And -50.19 degrees, if you didn't give me a reference angle, if you said -50.19 degrees off of the negative x-axis, well, what you're telling me is this angle here. You're telling me that the vector is down here. If you just tell me angle of -51.19 degrees here, sorry. If you just tell me -50.19 degrees without any reference to an axis, then your angle is actually down here using global coordinates like that, and the arctan function assumes global coordinates. So we cannot do that. If you are using arctan function, you cannot just blindly throw numbers into the equation. That is how on my exams you get something wrong, and that is how as a practicing engineer you may kill someone. So be very careful. So how do we do this the correct way? Doing this the proper way. And there are many ways to do it properly, but let me just illustrate one way to do it properly. The A, the actual magnitude of that, that's not going to change. That's just going to be the same 7.81 newtons. Again, magnitudes are a very forgiving process. You can do them with negatives without, it's going to work out just fine. But for the angle, for the theta, when finding theta, use reference angles only and positive values for your components. Use positive values only. So what I'm going to do is I'm just going to say, look, let's not think too hard about this. I have 6 and a 5. Just treat it like a triangle of where I have 5 along the x-axis and 6 along the vertical. 5 and 6. And I am looking for this theta here. This theta here. And theta is equal to the inverse tangent of, and this would be a reference angle again being measured off of the local x-axis, positive or negative, and so that would be 6/5, and the inverse tangent of 6/5 is, of course, 50.19 degrees. And so that means that this theta right here is 50.19 degrees. And if I want to use, I could then report my answer 2 different ways. One, I could use reference angles. I could say vector A is equal to 7.81 newtons at an angle of 50.19 degrees above negative x-axis. above the negative x-axis, or I could use absolute or global angles, or standard form, or whatever you want to call it. And to do that, I would say that I'm measuring the angle off of the positive x-axis, and that would be 180 minus 50.19. Let's throw that into a calculator. 180 minus 50.19. That comes to 129.8 degrees, or 129.81 degrees. If I want to use the same number of sig figs, 81 degrees, or same number of decimals at any rate, 121.81 degrees. And so, 121.81 degrees, and then absolute slash global angles. So I could then say that vector A is equal to, maybe I could use brackets for the global angles, 7.81 newtons, comma, 121.81 degrees. Either one would be proper, and really pinning down where exactly this vector is along the xy plane. So if you're not familiar with that, or can't remember that from, or haven't remembered that from pre-cal and that's still giving some problems, please review some old pre-cal texts or some materials online. There are plenty of, the good thing about being in the current year is that there are plenty of great online resources available to learn about and review things, even if you've seen them many years ago. You can find great resources from converting from Cartesian to polar coordinates, including more further discussions of this. All right, that'll do it for this portion of the lecture. I just wanted to describe not just what a vector is, but how to represent them in both polar and rectangular form, and how to convert between these. In the next portion of the lecture, we will look at how to apply basic vector operations, and mainly basic vector addition, subtraction, etc. All right, that'll do it for now. I will see you in part 3, and thank you.